Hello, my name is Ole Winther. I'm going to give this keynote at MLSP 2020. I'm just going to share my screen. This one. Share. No, that was not the right one. What happened? Is this the one? Okay, yes, that's the right one. So I'm going to present my talk, Latent Variable Models for Independent Component Analysis. Sorry. Going to present my talk, Latent Variable Models from Independent Components to Variational Autoencoders and Flows. Yes. Okay, this doesn't work. Yeah, okay, go. Yes, so the motivation for this work is that we often in machine learning work with high-dimensional data. So this is an example of a biological data set, single-cell RNA sequencing data set. So what you see here on the x-axis in the columns, that's all the different genes, and the rows, that's each of the cells that we have recorded the gene expression from. And all the gray, that is zeros, so that is kind of the specific genes that we haven't counted in a specific cells, and the blacker stuff, that's expressed genes. And what we would like with a data set like this is to find covariation patterns in this data set. So we would like to find genes that tend to go up and down and down and up and down together in the different cells. Yes. Another example of what we want to do with high-dimensional data is to find some lower-dimensional manifold that can represent the data. And here's an example of a data set of faces recorded, and you can see if we kind of zoom into different points in the manifold, we get things that are similar. So we'd like to find methods where we can actually take the data and go to some representation, some manifold representation of it. Another thing we would like to do with unsupervised methods is that we want to train a model so we can synthesize new data. So for example, the famous MNIST data set, we might want to train a model on that and then be able to generate new handwritten digits. So one model for doing this is what is called a latent variable model, and I'll just explain that and go through some of the classical linear latent variable models. And a latent variable model is a so-called generative model, so we can cite here Feynman, who said that what I cannot create, I do not understand. So a latent variable model, I can take this drawing here from OpenAI's blog, where they kind of have a cartoon of how a latent variable model works. So first you have some latent manifold, for example, a Gaussian manifold that will generate a latent variable C, and then you have some transformation from this latent space into the data space. So it means that we actually take this distribution, Gaussian distribution here with this circle, illustrated with this circle, and then we manipulate that in some way so we get a distribution in the data space that might be more complicated. So you can write that formally as you have this two-step procedure where you first draw a point in the latent manifold and then you transform that point, also possibly stochastically, to a point in data space. And then when we train these models, then we'll have observation in data space and we'll try to learn this model such that the model here in the green will assign high probability to all the data points we have observed in data space. So we don't observe anything in the latent space. I'll come back to how you can kind of interpret the latent space in a minute, but it's just for now construct that we use to be able to have more flexible distributions in the X space, in the observed data space. So in the gene expression example, X will then be a very high dimensional, maybe 20,000 dimensional vector of expression values for the different genes. And in images, it is like the pixel values in all of the pixel positions. Yes. Yes. So here's an illustration of a deep generative model. So you can imagine that we have a training set, again, our MNIST. So we have binarized it. So it means that it's only 0 and 1s. There's no grayscale here. Then we have chosen a dimensionality of our latent space. In this case, it's 2-dimensional. And we assume that we have a normal distribution, just a bivariate normal distribution with unit covariance as a prior distribution in the latent space. And then we have some model also for X for our observations. So we assume we have pixel index J. We have example index J and we have pixel index K, and we assume that we have a Bernoulli process. So it means that actually we kind of flip a coin, and we flip a coin with a probability given by this F here. And this F is a function of the latent value. So if we have a point in the latent space, then that will transform to a probability for this coin flip. And this latent vector here will be kind of shared, so it kind of can capture covariation such as that nearby pixel values will have a high probability to be on at the same or off in the same image, in the same digit. So if you want to have a deep model of this, then it's kind of straightforward. You can define a neural network model that will take you from the latent to this function here that defines these probabilities in the Bernoulli draws, right? So you go from this 2-dimensional latent space up to this 700 something dimensional X space by choosing the dimensionality of these weight matrices here, and tan H and sigmoid to be understood as element-wise operations. So let's say that we now have some scheme to train this model. Then we can actually synthesize data. We can, for example, then draw from this Gaussian prior distribution here, and maybe we get this point, so that is illustrated with this red point. That will give rise to an F function. So I'll show you like here, that this is the F for this specific position. And then, so that will give us kind of the mean. So what we've illustrated here are the mean probabilities that this specific pixel is on. But we are not done yet, because in order to generate the data, we actually have to flip a coin with these probabilities, and that gives rise to this more kind of not so nice looking image, but it's kind of following the kind of probabilistic model we have. We can do this again. We draw a new point down here now, and this part of the latent space represents 7s, and then we can generate a 7, and we can take a new point over here, and that will represent an 8, and we'll get this generated data point. So of course you can imagine that if you think about MNIST, then only 2 degrees of freedom is too little to actually represent the natural variation you have in digits. You have different digits, first of all, and you have different writing styles, kind of the slope of the digit. You have different thickness of the pen and so on. And the latent space should actually capture all this variation, right? So we don't have an observation for the thickness of the pen. So in the latent variable model, we hope that the latent space can capture all these sources of variation. So what are the goals of unsupervised learning? I've already talked a little bit about that, but I found this nice paper, recent paper, where it's kind of made into 4 points. First of all, we would like to capture the potentially high-dimensional data distribution, P of X. We'd like to be able to synthesize, to generate new samples. We'd also like to learn new features, as in this manifold example, so we have some representation in maybe a lower dimensional space of the data. And we would also like to learn maybe interpretable latent codes for the generated data. So this is tightly connected to the concept of identifiability, meaning that if we have or you can say in a way that the latent representation up to some trivial transformations will be the same if we train the model again with different random seed, more or less. I'll come back to this point a little bit later. So the game plan for my keynote here today is first to talk about linear latent variable models, time-honored models that have been studied for a long time, like principal component analysis and independent component analysis. Talk a little bit about that it's actually possible to have identifiability for nonlinear models. Then I'll move on to talk a little bit about flow models, which is a specific way to realize these nonlinear latent variable models. And finally, I will talk about variational autoencoders. I will show an example where we apply them to this single cell RNA sequencing data that I motivated in the beginning. And then I will also mention some new cool developments in the fields, which I think is a very fast-moving and interesting field. Yes, so let's start a place where we probably all of us are familiar, principal component analysis. So in principal component analysis, we form the empirical covariance matrix of our data. Here I assume that we have centered the data, removed the mean. And what we can formulate principal component analysis in different ways, but one way to look at it is that we actually solve the eigenvalue problem for the empirical covariance matrix, right? So X is our data matrix of size n, the number of samples, D, the number of dimensions of the data. And we are looking then for the eigen vectors corresponding to the largest eigenvalue. So that means the directions in our X space with most variance. So this is illustrated here in 2D. And if we want to kind of have a representation for this data, then we project onto these dimensions, and then we also scale with the square root of the eigenvalue. And this can be realized through singular value decomposition in an efficient way, but that's another story. Yes, so if you think about latent variable models, we already talked about MNIST, that it could be, the latent variable could be interpreted as for example, the writing style or the thickness of the pen or the what digit we have, I mean between 0 and 9, but it could also represent other degrees of freedom, such as some translation and rotation. So what we would like to do is to write down a latent variable model that actually can potentially capture these latent features in the space. So we have some parameters of the latent variable model, and then we have this latent representation of the data. So parameters will be shared between all the data points, but the latent vector will be specific for each data point, right? That's why I have this index n on the data. Often we'll start out with a linear model. That's a very good idea in many cases. So we can take one model here where we say that there's a linear relationship between the latent space and the data space, and then there's some kind of residual noise E that cannot be explained by the model. So it turns out that principal component analysis can actually be given an interpretation in terms of such a linear latent variable model. This is an old result, but that doesn't make it worse, from Tipping and Bishop in 1999, where they considered a model like the one on top, and then they make a very specific assumption that the prior or the latent variable is a normal distribution with unit covariance, and that the noise is also Gaussian, additive, so the noise is Gaussian with a diagonal covariance with variance sigma squared. So if you take these two assumptions, then you can actually go and calculate the mean and the covariance of x, right? So you can find the mean value, the expected value of your data points, and you can also find how you expect that the different components of x co-vary. And this is not a very difficult exercise because everything is Gaussian here. So we add up two Gaussian signals. W is a parameter, so it doesn't have any distribution in this formulation. So the mean value is 0 because the mean is the sum of two mean zero variables like this, and the covariance is, you can see according to this line, is simply given by W transpose plus a diagonal corresponding to the noise term here, right? So we have no dependence between the latent and the noise. So this means that since both C and E are Gaussian, then X will also be modeled as a Gaussian. So we can actually write down the likelihood for one data point is a normal distribution with this particular form for the covariance. So far we've just kind of written down the likelihood for a particular latent variable model, but what now becomes interesting, and which is kind of the contribution of Tipping and Bishop, is that they actually showed that if you do maximum likelihood estimation on this likelihood, then you will kind of come back to principal component analysis. Of course, intuitively, it's not so strange, because if you think about it, we have some empirical covariance here, and we have a model for the covariance here. And in order to kind of make this model fit the data the best, then this model covariance here should capture as much of the variation in the data as possible. And this is actually also what is shown. So if we have M kind of components, so it means that the size of W is D, data dimensionality, times M, then actually W will span the M first principal components that we know from PCA. And then the variance here, this maximum likelihood estimate of the variance here, will correspond to kind of the sum of the eigenvalues, the remaining eigenvalues from M+1 up to D. Yes, so that shows that there's a deep connection between generative models and principal component analysis. And it's also like a nice example of like how we do modeling, right? That we don't have a free covariance, but we actually have a structured model for the covariance. But there are some limitations of PCA. So if we try to solve the cocktail party problem, so that means that we imagine that X is now the recording of some, for example, stereo recording, and we have two speakers, for example, or three, and then W then is the mixing kind of corresponding to kind of the path of the sound from the speakers. Then we arrive at this linear model with some, of course, some obvious simplifications. And this looks like it's something that we could use PCA for, right? So we can actually try to use PCA for this, but as you probably know, this is not possible, because if we see that the solution we get is not really working so well, because if we look at the structure of our model for the covariance, we can see that we can actually rotate W like this. So U is a rotation matrix, and if we insert that in the covariance, then you can see that we actually get the same covariance, because it only depends on W times WT for a different W matrix, right? For this rotated W matrix, and that means that we can actually kind of also rotate the sources kind of in the opposite direction, and then they are not unique, right? And this, of course, has to do with the way we chose the model, that we chose a spherical Gaussian as our prior. So that means that it has no preference for any direction. So probabilistic PCA does not work for solving the cocktail party problem. But we have other methods, independent component analysis. So what we need to use is prior knowledge, and of course also some properties of the nature that we model. And luckily for us, real sound signals are not Gaussian distributed. So we can make a small example here and kind of simulate two heavy-tailed signals, C1 and C2, and plot and have some W, sorry, this should have been a W2, some two W vectors, W1 and W2. And then if we plot that data in X space, so we actually kind of realize the C1 and C2 and plot X, then you can see that we get these kind of tails sticking out corresponding to the heavy tails of the distribution of C1 and C2. So actually, if we want to model something better, we actually have to modify our prior over the manifold. So we could, for example, here have some distribution with a more heavy tail. And this is, for example, what has been done in the very famous Infomax algorithm from Bell and Sarnowski. There they assume that W is a square matrix, so you can have two speakers and two microphones, for example. And then you can actually, for this model, and you also assume that there's no noise in the recording. And for this model, you can actually, as shown by Mackay in 2003, you can actually derive the exact likelihood. You can do that by saying that the likelihood for such a degenerate model here without noise is just a Dirac delta function. And you can do a change of variables. And then in the end, you find a likelihood function for this data point, which is given by this expression. You can see this P here is the prior distribution over your latent variables. So here you can actually insert some kind of heavy tail distribution, and then you can optimize this, maximize this likelihood function over the data set of these data points, these recordings at the different time points. And actually, just to connect a little bit to something I'll say later on today, is that this is a flow model. This kind of way of formulating a model where you have a deterministic mapping between the latent and the data, and you have a prior over the latent. That is what we nowadays call a flow model. And what is kind of new in today's flow models is that you can actually make this mapping here non-linear, but you still need to make it invertible, like you can see the property we used here, that actually we can invert W here. So that also requires that W is full rank. Yes. Okay, but now you can ask, I showed this example in the beginning with this nice binary MNIST generative model with a non-linear coin flip probability here, this F of C. Is that model identifiable? And in general, the answer is negative, no. So that means that actually the latent space we find is not unique. If I kind of run my learning algorithm that I will talk about later today with a new random seed, I can find a new latent representation. But there's been some very interesting recent work where it has been shown, proved mathematically, that if you extend your latent variable model to have a latent prior that is conditioned on some observed variable U, then in some cases you can actually have identifiability. And I'll just show a small example from another paper where this is the case. So here is a simulated data. So it's two-dimensional data, and you can see you have like now U is like a class index, and in this example you have 1, 2, 3, 4, 5 different classes, and each class has its own mean and covariance for the latent variable for that class, right? So it means that this kind of the red class, it has this mean, and then it has this standard deviation in this direction and this standard deviation in the other direction, and the same is true for this. So this is a model where we actually kind of know something more about our data. We know that that what data point, what class our data point comes from, right? So it will also be MNIST, where we actually know where the digit comes from. Under this condition, and with algorithms proposed in these type of papers, then you can actually show that you can learn this model and you can recover the original distribution up to some trivial transformations, such as you can see here, an overall global rotation of the data, and maybe kind of a flip of the axis. If you run the variational autoencoder algorithms that I'm going to talk about later today, you don't see this identifiability. So yes, identifiability is possible for nonlinear latent variable models, but you need to condition on additional information. Yes. So this was part 1 about the linear latent variable models and their limitations and strengths. Now I'm going to talk a little bit, a short while, just about the flow models. And then afterwards about the variational autoencoders. So just to kick it off, let's have a small kind of overview of the different popular deep generative models we have nowadays. So we have the latent variable models. So I will talk about variational autoencoders here today, but also deep Boltzmann machines and that kind of models is an example of latent variable models. For the deep Boltzmann machines, then the latent variables are discrete, and in the variational autoencoders, they are usually continuous. Not always, but usually continuous. Then we have autoregressive models. So autoregressive models, there we use the chain rule of probability to write the joint distribution of all our dimensions as this kind of chain of conditional probabilities. And of course, we can choose any order we want. So this is just like the natural order here, but we can have any order we want. And what I'm going to talk about today when I talk about flow models is actually this kind of famous PixelCNN model, which is a combination of such an autoregressive model and a convolutional neural network where we use masking to achieve this autoregression. I'll show that you can actually formulate a flow model which is equivalent with the PixelCNN model. And of course, this is interesting that there's these kind of relationships between models, but it also has a practical consequence that we can actually now synthesize data we can do that already with the PixelCNN. Sorry, it has the consequence that we can find a latent representation of our data and do manipulations in the latent space of the PixelCNN, and that was not possible if you just formulate the model as an autoregressive model. So flow models, just to kind of generalize what we did when we derived the Infomax algorithm, they go like this. So we have a prior distribution over our latent space. We're free to choose that different ways, and then we have a deterministic mapping from the latent space to the data space. And there's like one important restriction on this, and that is that we actually should be able to also calculate the inverse of this one. So that means that the dimensionality of X and C have to be the same. And that is not the case in variational autoencoder. You could see the example I gave with the binary MNIST. There we actually went from 2 dimensions up to 700 something dimensions. So this gives like a restriction, but it also has the advantage that you can actually calculate the likelihood probability of the data. You can calculate that in a closed form like this, where this term here is the Jacobian of the mapping from the latent space to X. So I should also mention that we have there are also deep generative models that are non-probabilistic. All these are probabilistic with a likelihood function. There's the generative adversarial networks. I will not talk more about that today, but it's an important class of models. Yes, so I'll talk a little bit about some work we have done in my group. So it's my PhD student, Erik Nielsen, who has worked a lot on these flow models, have some nice work, and I also linked to his GitHub repo in the end of the talk. Yes, so we want to look at problems where we work with what we call quantized data. So that means that we have some data that is naturally continuous and then we discretize it. So you can think about this as images where we have pixel values that are usually quantized to discrete numbers between 0 and 255. So flow models naturally work with continuous data. So in order to apply flow models to this kind of data, we do what we call dequantization. So that means that we take the quantized data, or sorry, the discrete data Q. So that could be these numbers between 0 and 255, one of these numbers, depending on what pixel it is. And then we add uniform noise, and then we normalize it so that we actually get here X to be between 0 and 1. Now we can define a flow model on these X's. And you can say why, what is so strong about this? It can be quite strong model if we use an autoregressive model. So that means that we actually find dependencies between the different pixels by conditioning on the previous values of the pixels. So so that means that we can let each of these if we wanted, we could make each of these conditional probabilities be a flow, or we could also, in some models like the so-called flow model, we can also model this as not being autoregressive, but simply like joint distribution through suitable transformations. So in PixelCNN, we treat in the PixelCNN paper, they treat pixel values in a very simple way, simply as a categorical distribution, right? So that means that each pixel value will be a 256-way classification problem. So you kind of classify you predict pixels by classifying, given the previous pixels, what is the pixel value here? So what my PhD student did was that he realized that you can actually make this into a flow by the following operation. So you assume now that your prior distribution or your latent for each dimension is just a uniform distribution. And then you can define a transformation from this uniform noise into a piecewise continuous distribution by learning kind of these values here, how this kind of that maps this uniform noise into this continuous, right? It's kind of these slopes here. Each slope is described by one number, which is essentially like these pies here, and then this continuous distribution you can use directly on the categorical data like this. So and with this construction, they could actually prove that the likelihood function you get from this with this kind of construction and the likelihood function you get for this categorical formulation is the same. So that means actually that these two models are the same, even though one is kind of purely an autoregressive model and the other one is a latent variable model with a uniform distribution over the latent variables. So now we have this model, so you can kind of go back and say, okay, we actually have this flow model where we can now, we know that this is a uniform in the number of pixels dimensions, and we can then draw samples, for example, from this uniform, and then we can put it through our learned transformation, and then in that way we can actually generate new data. And another thing we can also look at is before we do that, we can also look at whether this model actually have transformed the original kind of histogram over pixel values that looks like something like this into a uniform data, right? So if you look at this, if you go from the, if you go here from X, if you take an image and then you go back and you kind of apply G to the minus first, and you get C, and then you plot the histogram of C given a lot of images, then this should be uniform if the model has worked well, right? That's how you get a high likelihood. And that's what you can see here, that it has actually approximately made this to a uniform distribution. I should say this plot here is for a different variant of these PixelCNN models, so that we can also treat. And you can see it almost achieved it. It's a little bit complicated because you can see also in real data you have like an over-representation of black and white pixels. Yes, and here's some examples where we actually take an image from, I think it's CIFAR 10. So these are kind of low resolution images. So that's not our fault that they don't look so nice. And then you can see this is a latent representation of this. So an image here is, of course, like in each pixel, you have 3 color channels. So we can actually also kind of visualize the latent representation as an image that looks like a kind of things you get on an old type television if there's no broadcast. Yes. So this is quite nice, and maybe one of the things you can see is that if this model had worked perfectly, then this would be completely like a white noise in this representation. But you can see, for example, that it's not completely white noise. You can see, for example, here this thing here in the front of the beagle. You can see that in the image still. So the model has not been able to completely remove the spatial signal from the data. So it's not a perfect model, but it has achieved something, and we can calculate kind of a normal measure of how well these models work is that you measure the number of bits per dimension. So that's on a test set, and that's a kind of a measure for how well it works, and small numbers is best. So this PixelCNN is one of the state-of-the-art models. Yes. Another thing we can also do is that we can actually take 2 images and we can then find their latent representation, and then we can make an interpolation between these 2. So this is what we have done here. This is just an equation to show that you have to be a little bit careful to actually kind of, when you do the interpolation, you have to interpolate in a high probability regions. You can find that in our paper. But here you can see how Dirac interpolates between 2 images of trucks. And if this is a really good model, then any image in the interpolation path will also look like a truck. And this is not completely the case, but it's kind of making some sense, at least what it shows here. We have some more images here of interpolation between 2 birds. They are very different. So I don't know what to say about this. 2 ships maybe works a little bit better. I don't know. Yes. So that was what I wanted to say about flows and their relationship to autoregressive models. Yes. So the last thing I want to talk about is variational autoencoders. So to go back to what we talked about with latent variable models, you have this 2-step procedure when you generate data. First, you draw a point from the latent manifold, and then you transform that point to the data manifold. And that means that kind of multiplying these two together, you have a probabilistic model for the data and its latent representation. And again, as I said before, it's important to stress that latent variables are different than parameters, because for each data point you have one latent representation. And the latent representation is not observed, so it actually acts as what we call nuisance parameters. So in order to calculate the likelihood, then we have to integrate it out. And this is where we kind of pay the price for a flexible model, because this integration is only possible for very simple models, like for example, probabilistic PCA. So we have to pay some price in terms of approximation. And that I will talk about in the coming slides. But just to motivate a little bit, this is work I did with one of my other PhD students, Christopher Grønbæk, on using variational autoencoders for single cell RNA data. Single cell RNA data, as I described in the beginning, is data that is sparse, and it's count data. So we should try to make our latent variable model work under these conditions. Yes, but before we do that, I mean, let's first define the prior distribution. So one prior we have seen multiple times now is just a Gaussian distribution over the latent manifold. But if we expect to have some kind of clustering in the latent space, for example, when we talk about our single cell data, it could be that actually these cells represent different cell populations. So we have some degree of clustering corresponding to different cell populations. Then we can put that into the prior. So we can, for example, define a mixture distribution in the latent space. So that means that we have these clusters, and this is a prior cluster probability, and then each cluster is a Gaussian, but with different mean and variance. So it means that we actually can kind of learn the position of the different cell types, for example, in the latent space. So that means that M and V and these priors, that's additional parameters in our model. Yes. And in order to model count data, we need to have a likelihood function corresponding to count data. So one example of that is a Poisson distribution. So that means that we model our distribution over the counts for each gene. So we have D genes. So we have a Poisson distribution for each of the genes. And the Poisson rate, so the parameter in the Poisson distribution, depends on the latent value here. And we could, for example, have a very simple linear model here. Since the rate should be non-negative, we have to apply nonlinearity like the rectified linear, the ReLU. But we could have a linear. Apart from that, we could have a linear model between the latent and this rate. Yes. So this is a way to actually kind of try to build in a little bit of biological knowledge and property of the data by having, for example, a clustering prior corresponding to we have different cell types, and then in order to model count data, we actually put in some count, some discrete distribution over counts. Yes. So how do we treat this intractable marginalization over the latent variable? We use the variational inference. And the idea in variational inference is, instead of having to do this integral over the latent, we would like to have an integral over the log of the distribution, because it's easier to kind of integrate over logarithms than integrating over distributions like this. You can imagine that this distribution is very spiked around values of C that explains the data. and it's very hard by some kind of random sampling method to actually find that point. So what we do in order to get the log is that we apply Jensen's inequality to get a lower bound on the likelihood, on the log likelihood for this. So this should be an x. This is another error here. This should be an x. So we introduce this approximate posterior distribution. We call that Q of C. So there's one Q of C for each data point. And then we have to, again, integrate still over the latent variables like this. But for some models, this is actually possible to write down the closed form solution of this because we have the log. And for other models and for modern models, we will use sampling to do that. There's also another important modern trick that we apply in variational autoencoders, which is called sometimes amortized inference. And that means that now this variational distribution, instead of having a variational distribution and learn one for each data point, we now have a variational distribution that learns that is shared between all the data points, but then takes the data point as an input. And we can achieve that, for example, by saying that this variational distribution is a normal distribution, but then we learn a mean function and a variance which we parameterize as a neural network that maps a point from the input space to a mean value and a variance in the latent space. And then the final thing we do in order to make this equation here useful in modern automatic differentiation frameworks is that we first of all approximate this with a sample average. So we sample from Q, and then we use the so-called reparameterization trick in order to be able to actually differentiate between, with respect to the parameters of this inference network, right? So we have parameters here in this neural network mapping, and then we have finally, in order, because C is now not deterministic but stochastic, we then draw from a 0-1 normal Gaussian distribution here in order to actually draw a random sample from the latent posterior latent space from this Q here. So that is a very brief description of variational autoencoders. You can go to these references for more details. But you can see now we have actually, in this case, we have actually like two networks. So that's why we also sometimes call it an autoencoder, because we have first this network that stochastically encodes the data. So that's the encoder. And then this network, we can look at this as a decoder because it maps from the latent manifold back to the data space. Of course, when we train the model, we know X, and then it's a question about actually taking this, doing the mapping here in Q to C, and then back to X, and then checking by calculating the log likelihood, how well does the model describe the data, right? Yes. So now we have trained this model on a lot of cells, and now we can calculate the lower log likelihood lower bound. We can also do that on some held out data, and now we can repeat this procedure for a lot of we can repeat this procedure for a lot of different likelihood functions, right? I just mentioned over here the Poisson, but we could also take some more flexible models, maybe some models that are better suited for data that has a lot of zeros. So for example, like a negative binomial. And then we can calculate the log likelihood lower bound on a test set, and then we can compare, see what model did actually describe the data best. And you can see that here for a specific data set, we have here on the x-axis, we have plotted the log likelihood lower bound on the test set for different models. So that's shown here. And this on the y-axis, not so important here, but that's a measure of how well we actually recover some ground truth labels in the data. And you can see here what is important for this thing here is that actually this orange corresponds to the negative binomial. So that means that this we can actually use this test set to actually find out what link function, what likelihood function works best for this particular data. And that gives us some insights in the distribution of the data. We can also visualize the latent space. Of course, now, as you know, this is not trained. This is trained completely unsupervised. So this is not an identifiable representation, but you can see using these ground truth labels that has arrived from cell sorting, sorting the cells before we did the expression, that actually the model is pretty good at recovering the original types in cell types here. And here we have used a t-SNE plot, and that's not because we especially favor the t-SNE plot, it's simply because the latent space is 50-dimensional in this case, and that we cannot visualize, so we need an additional method to get it down to 2 dimensions. And we could have used PCA or t-SNE here. Yes, you can see there's some overlap between some types, but that's also something that biologists tell me is what to be expected. Yes, we can also go in and interrogate particular latent factors, and you can see that also just taking the 2 first latent factors, we can see a pretty good separation of the data. We can also apply this to a different data set. This is no longer single cell, so it's no longer a particularly sparse data set. This is a big pan-cancer data set called TCGA with many different types of samples from tumors. You can see the different types of tumors here, and you can see also that we have a pretty decent clustering of the different cancer types in this example. And just to make a sanity check, we can also take a linear model, a linear generative model, like the one I described when I introduced Poisson distribution, and you can also see that it gives quite similar kind of clustering of the data, maybe not as good, I don't know. That's something that we can actually use this log likelihood to determine whether it's better to use a linear model or the non-linear model. Yeah, so that was a little bit about how to use variational autoencoders in a biological application. I also have a few more slides about some cool new variational autoencoder applications. So one thing that has been like a folklore in the generative modeling community for some time is, at least if you look at images, these generative adversarial networks are better at generating kind of something that looks like real-world data. Then recently, 2 researchers from NVIDIA challenged this with this nouveau VAE, which is like an upscaling of some of the concepts that have been around in variational autoencoder modeling. And I think this is on this famous celebrity dataset, and this is generated data. So this is not some data that's in the dataset. These are synthesized samples. They prove in that paper that you can actually get something that works as well as GANs if you do it the right way, and that's kind of scaling up is one of the ways to do that. Here are some other kind of things they have done. One of the things is something that I'm pretty happy to see, is that actually something that one of my former PhD students did during his PhD with the latter VAE, to have a model where you are kind of your encoder. So you can see here X here going up towards kind of a hierarchical latent representation. Your encoder model shares some of the backbone with the generative model. So this is the generative model you have here. The blue is some part of you can see the C's here. This is kind of again a hierarchical generative model, and this part of the model is shared between between the generative model and the inference network part. And these R's here represents like pretty big residual block elements in the architecture. Another very nice demonstration of ideas in variational inference, maybe not so much VAEs, but closely related to VAEs, is a very recent paper on denoising diffusion probabilistic maps. And the idea there is that we now have our data, we call that x0, and then our latent variables, we call them x1 to xt. And we now have a generative model where we essentially take kind of white noise, and then we transform that with a suitable mapping into data. And we use this kind of variational approximation where we also have an so you can call this like it's the decoder. The generative model is a decoder, and the encoder is a variational distribution that kind of runs in the other way. So that's essentially a model that takes data and then slowly transforms that back layer by layer in this hierarchical manner into noise. And formally, this is written down like this. So we have the white noise, xt. So that's simply drawn from a, oops, another typo here. It's just drawn from a normal distribution with zero mean and unit identity covariance. And then we have this kind of autoregressive or in-depth autoregressive model where we in each step learn a mean function, a covariance function depending on, sorry, this should be a T here, another typo. We learn a mean function, and this is like a neural network model that maps xt to the mean value of xt minus 1. And then the encoder that transforms the data to noise is simply a kind of a random walk Gaussian distribution. So this corresponds to, and then you write down the variational lower bound to the log likelihood, and this corresponds to a VAE, where you can see the latent variables are these x1 to xt, and then the encoder is a very simple kind of Gaussian random walk. So it has been demonstrated in this paper, recent paper, that this works very well as a generative model for images, maybe on par with the VAE we saw in the previous application. But it's also even more recently been applied to generating audio. So this is like a non-autoregressive generation of audio, like a speech synthesizer. That is not autoregressive, and that's a big advantage because then it's much faster to actually generate if you don't have to do it one sample at a time. So it's like what I described before, that you actually can start with random noise, and then you can layer by layer kind of shape that noise in order to get a waveform. And this is like a zoom in on the waveform for a short window, and this is on a longer window. And then when you want to do speech synthesis, you actually can kind of condition this model on additional features, like for example the content of the text. I should also say that these models, actually it's been proved that they are very close to this famous score matching method. Yes, okay, so that was all I wanted to say today. So just to sum up, my points for today is that it's possible to extend linear latent variable models to become nonlinear, and they are most often non-identifiable, but that doesn't kind of stop us from actually interpret the latent space anyway. But I think maybe in the future we'll see more work that pays attention to these proofs on identifiability in nonlinear ICA type models. I would say that in my impression, of course I'm biased because I'm working in this space, but I would say that there's been a lot of important work the recent years in deep learning on unsupervised learning, on modeling high dimensional distributions. I think this field is starting to become mature and even though we like to apply this to kind of images, I think we will also see a lot of these things in, for example, speech processing and so on. I would also say, again, a little bit biased, but I would say that variational inference is a very powerful way to actually think about problems. For example, with this score matching, I think it's very nice to see that there's actually a well-defined likelihood lower bound corresponding to that method. And I think also we're going to see a lot of nice use in signal processing of these methods. And finally, here are some links to GitHub for the work from my group I presented. Yes, now I will stop sharing the screen. And I'll go back here and just say, oh, I hope I've been full screen. Let's see. I'll say thank you for listening, and it's been a pleasure to talk about this. I really hope that in the end, it should not be, it will not be a pre-recorded keynote, but it will be a live recorded keynote, and I hope that there will be a lot of questions on this. So thank you.